My name's Terry Busk. I'm with the American Institute of Mathematics. And we have Scott Kim. So Scott Kim is a prolific puzzle designer and game designer. He's also the creator of Math Monday, which I had the pleasure of helping him out with over the last couple months. And he's going to be leading us in the game of life. So Scott, take it away.
Hey guys, glad to be here. Thank you all for coming. I hope you're enjoying the week. So when I was asked to talk to the math teacher circle, I thought the thing I most wanted to talk to you about was Conway's Game of Life. Now I'm curious, how many of you have heard of Conway's Game of Life and know how it works? Can you type yes or no in the chat? Yes, no. We're getting both yeses and nos, maybe sort of some of each. Okay, that's great. Then some of you will have seen it before and some not. Let's see. So a little bit of history. The Game of Life. Let's see, I need to find where my tab is. Just a moment. Here we go. Was invented by a mathematician named John Conway. Conway passed away recently, unfortunately, but I had the pleasure of knowing him. I'll talk to you a little bit about him. Then I'll talk about the rules of life, and we'll play it on paper, hopefully. So for that, you will need a piece of paper, a pen, and some markers. Or some, I'm going to be using, you basically need checkers and some little objects to put on the checkers. I'm going to use these pawns, but you could use beans or something like that. You'll need this to play it. So you can use a coin, you can use a checker, you could use a little square tile. If you have manipulatives at home, you could use those. I'm going to continue talking, but please have these available. We'll be using them in a little while. You'll need about 10 of each, 10 coins and 10 little things. Almost anything will work for these. We're going to play it on paper, then we're going to explore life online. And both of these events, you'll be working with other people at tables in Remo. Then we're going to talk about the limits of life, go even further and talk about it's the background of cellular automata and computation. Okay, so that's a little bit of an outline. Let's talk about John Conway. Conway, if anybody was a rock star in math, it would probably be John Conway. And it's not just because he was born in Liverpool, England. It was because he was a flamboyant personality who just loved an audience. And everywhere he go, he had the marvelous quality of, if you were in the room, he wanted to connect with you. It didn't matter what level of math you were at, he would show you something that would be of great interest. And he put as much work into how he presented ideas as he did into figuring out the mathematics itself. Very quality I very much like. So the answer to who is your favorite mathematician? Well, actually, I'm kind of curious. Before I go on, who's your favorite mathematician? Why don't you type that in the chat? I'll see what people think. And Terry, if I'm doing anything wrong, please let me know. Don Knuth, yeah, that's definitely one of the greats. Don also straddles computer science and mathematics. I asked the question about favorite mathematician. I like asking it to kids because they may not have ever thought about it that way. Everybody has a favorite musician or band, but not everybody has a favorite mathematician. Well, anyway, here's so you get to know him. Here's some pictures of John. His office at Princeton was full of models. He never knew where anything was, fitting all too well into the absent-minded professor stereotype. Here's he would get down on the floor. He made models all the time. Here's a cartoon of him with this figure is called the Alexander Horn Sphere. So this was the Conway Horn Sphere. And there's a number file video of him. Here's my tribute to John. These patterns are all patterns in the game of life. So this is John Conway spelled out in life itself. You'll be seeing how life works in a moment, but that's my little tribute to him. He's best known probably for studying games and puzzles. Did a tremendously deep study of a lot of children's games. You can see down here, here's a variant on chess. There's some games like dots and boxes or jumping peg puzzles over here. And he went way deep into the mathematics. I had the pleasure of designing some book covers for him. Here's one of his best known books on numbers and games, which I heard he wrote in just a week or two, and a lesser known book on quaternions and octonions. Some of you have probably heard about quaternions. They're the next thing after complex numbers. Well, you can go even further. There's octonions. They're even stranger. At one point, John took a vow. He said, "Thou shalt stop worrying and feeling guilty. Thou shalt do whatever thou pleasest." Why did he take that vow? Because he was worried about his status. This is before he became famous, and he was thinking, if I pursue some of this stuff, that some people are going to think I'm doing something frivolous. Maybe I should do respectable mathematics. But he decided that you can find interesting mathematics just about any place. So he decided to not worry about what other people think and just pursue what was interesting to him. His biggest hit by far was The Game of Life. It was around for a while, but it became really public when it was an article was written by it, but in Scientific American, in Martin Gardner's Recreate Mathematical Games column. That quickly became the most popular article that had ever been published in the magazine, and Gardner did something like 4 or 5 follow-ups. He called it a zero-player game, and we'll go into the rules in a moment. It became so popular. You can see it's sort of a computer-oriented game, and a lot of people took to programming up versions of life, and it quickly became, I've been told, I don't know if this is still true, the single biggest use of computer time of anything, of all applications. I'm not sure if that's still true now that we have things like web search, but it was a big hit. That's the main thing. So let's get into the rules. I'm going to go over them on paper, and I'd like you to follow along with me. So if you haven't already, get some little objects, some checkers or coins. Get something to put on them, like pawns or beans. You'll need maybe 10 of them, and get some paper and pen. I've already drawn a grid. Okay, so let's. Terry, if you can help me out, I'm going to be using the webcam now. I see you have all 3 up on the screen. We won't. Okay.
So if you want to go with fewer cams, of course you have to turn them off. I can manually turn them off for you. So you can.
Yeah. Let's just use the document camera now.
So you'll have to turn off your presentation and your iMac camera.
Okay.
Unfortunately, I can't do it for you.
Got it. Okay, so I will go back to here, and I will stop sharing screen, and I will turn off my camera. That doesn't turn me off, though.
You're going to have to turn off your microphone, too. So something people in the chat can do is they can make you full screen, because now your microphone for the laptop's not on either.
I can turn on my microphone over here. Sorry about the feedback. Okay, am I audible, Terry?
Yeah, you sound great.
Okay, so let's play life. So life is played on an infinite checkerboard. I'm just going to play in this area. That's all the area I need of squares. And each square can have a piece on it or not. It can be empty or full. So if you haven't already, go ahead and draw some lines and make a little grid. Maybe 5 by 7 or so is all you need. And let's put some pieces on it. Now the rules of here, the general scheme is you're going to put some pieces on some of the squares, then the rules of life will take over and change this into another pattern, and then into another pattern, and so on. It's like you're setting up the primordial soup, and then you're letting life evolve. And here are the rules. If you've got some piece, I'm going to set them up like this. Here's a pattern. So I have six squares that are on and everything else is off. Now, the rules tell you who lives and who dies. So first of all, I have to say that each square has 8 neighbors. These are the squares that are adjacent by a king's move, either horizontally, vertically, or diagonally. So those are the 8 neighbors of that square. This is generation 1, this 6 square figure, and any checker that has only one neighbor that's a checker is going to die on the next generation because it's too lonely, or if it has no neighbors at all, it dies. So this one only has one neighbor. How many neighbors does this one have? Type your answer in the chat. I want to make sure that we're all understanding. Yes, everybody's answering 3. That's correct. It's a neighbor to this one, and then this one diagonally. If a checker has 2 or 3 neighbors, exactly 2 or 3, it survives. It's happy. So this one does survive because it has 3 neighbors. This one, however, how many neighbors does? Well, I'm going to point to this one. It's easier to see. How many neighbors does this one have? That's right, 4. And so if a checker has 4 or more neighbors, it's going to die on the next generation. So this one's going to die of loneliness. This one's going to die of overcrowding. What other checker is going to die on the next generation? That might be a little hard to describe in chat, but is there another one that's going to die? The one vertically next to that one, says Stephen. Yes, that's correct. This one's going to die. This one will not die. It has 3 neighbors. So the others are happy. So those are going to die in the next generation. Now there's one other rule, which is an empty square that has exactly 3 alive neighbors will turn on the next generation. So this is one of the squares because, well, all 3 of the squares above it are already on. So I'll put a yellow one there. This one's going to turn on the next generation. And if you've got beans or something like that, it's nice to mark who's going to die and where the births are going to happen. I use 2 different colors, but you can use the same color. Now, where is there another square that's going to turn on the next generation? See if you can see that. You can type it to the right. Yes, next to the yellow. Not this one. That only has 2 neighbors. But this one. Anything that's sort of next to a wall is going to turn on. Now, what other squares will turn on the next generation? Rebecca says none. Stephen says none. The central blue one. I'm not sure what that means. see, the central blue one, because it will have 4 neighbors. The central blue one will die. I wanted to know if there are other next to any other births. Okay, so you're chatting back and forth. Well, I'll just go ahead. These are the only 2 squares that are going to turn on the next generation. So we've this is how you play life by hand. And when the game was first invented, computers were pretty slow and or clumsy anyway. And the people who started playing life, John and his friends, played it by hand, quite a bit like we're doing right now. So for the next generation, these 3 are going to go away. So I'll take them off. And then 2 more are going to appear where these births are. So I'll replace those births with checkers. So I took off the deaths and put on births. That's the next generation. So here's the question. See if you can figure it out. What's going to happen on the next generation? Where are the births and deaths? You always start with 6 markers, Lee asked. No, you can start with any number. You could even start with an infinite number. But especially when you're starting off, it's good to start with a small number because if you're playing by hand. So Stephen says, death at the tail next to you. That's right. This one's going to die because of loneliness because it's only next to one other. So I'll put a blue here. What about births? You see any births? Birth next to the blue marker to your left. That's this square. That's right. Takes a little looking. That one has 3 neighbors. Yeah, next to the blue. That's right. What else will happen? How do you grow? That's an interesting question, Sue. You grow basically through births, but I don't think that quite answers the question you're asking. Yeah, that's right. Nothing else. There's no other births or deaths, so the next generation looks like this. And from here, what happens? We're going slow right now to give you a chance to just kind of absorb the rules. It becomes intuitive after a while. What is the grow rule? I see. Sue asks. A pattern grows by cells giving birth. So I'm not sure. The birth rule is the only thing that has to do with growing. And natural question is, are there patterns that keep growing? We'll get to that later. Anyway, that's it. Yeah, the birth rule is an empty cell that is exactly adjacent to 3 other cells that are already on. An empty cell next to 3 others will give birth on the next generation. Right here, there aren't any cells, but if this was occupied, then this cell would give birth because it's next to these 3. That's where. Okay, so nothing else happens. That's right. This is, in the jargon of the life aficionados, this is called a still life. It doesn't change. It just stays as it is. And it's been dubbed the small boat. That's a boat. Okay, so there it is, life in slow motion. I would like you now to, hopefully some of you, I guess I should ask, please say yes or no whether you have paper and markers like these in your possession. Say yes if you have it, and no if you don't. Okay, most of you, some no's. Looks like, okay, so what we're going to do together now is get together in small groups. Remo is good for that. Say groups of 3, and if hopefully at least one of you has materials, and you're going to explore what happens on your own to some of these other patterns. Now I'm going to need to switch over back here, so I'm going to just a moment while I switch.
Hey, Scott, would you like me to bring everyone back to the table view?
Okay, so on my slide presentation, okay, we went through the rules of life. Here, I introduced life as a game, but most games have goals to beat another person. There is no set goal for life. It's pretty much start with the pattern, see how it grows and changes. We just went through this pattern on the right here. This is generation 1, generation 2, and generation 3. And so I want you to take a look at these 4 patterns in your groups and see if you can see where they're going to go. Now, I think this screen's going to, switch off in a moment. So write these down before. I'll give you a minute to write them down, and then we're going to go into groups. We'll go into groups for like 5, I think about 7 minutes. I'll stop it and see how you're doing. And the question is, what happens to each of these patterns? And collaborate. You can help each other, check each other's work and see, or you can work in parallel and work on different patterns. And if you have extra time, you can explore some of your other patterns. Try making another pattern out of 5 or 6 dots and see what it does. Any questions before we go into groups? Any chat? You can chat questions. Okay, so Terry, please help me out. Let's go into groups, and I'll set a timer for 7 minutes, and then we'll come back.
And then
okay.
Oh, this
Mr. Recording is also here too.
Yeah.
Okay. So these 3, so we figured out that these 3 are just going to switch positions. So Terry, can you make those 3 go away?
I can make those 3 go away.
Excellent. And then we'll put up the next one.
Hey, Scott.
You dropped a little square on there too.
I did.
Yeah, I've been bopping around. Most people are struggling to use the whiteboard.
Yeah.
What?
Okay, so let me go to black.
You're
Okay.
right. So, see, I'm not seeing your whiteboard. Is that? Are you
So
using
it's
the whiteboard? There?
bottom right. Yeah, you have to click. You have to open it manually.
Oh.
Okay. Stop that.
What was our next pattern?
I'm
So
trying.
can we rotate? Can we rotate and go to another table? Kind
Sure.
of.
Yeah. Yeah. You go back to just double click on any
Okay.
table you want to join.
Double
Okay,
click
so
on the table on another. Okay. Right click or left click?
Double click with your left. Left.
Oh,
Next
left.
finger.
Well, you're already doing it. My suggestion originally was just do it with physical objects and point your webcam at
Right.
the stuff you're doing. This group wants to use the whiteboard. Actually, everybody wants to use the whiteboard. It's not just you.
Yeah.
Okay.
Okay.
So we have. Okay. So
So-
who's gonna die? Nobody. Nobody
Okay,
dies.
This guy has
No, these guys die.
1, 2. Okay.
No.
These guys die.
They have 2. Why did they die?
He's got.
Oh,
only-
they have 2 neighbors. My mistake.
yeah,
My
he's got
mistake.
2 friends.
So no one dies.
But we have growth.
Yeah,
'Cause
growth.
1,
Yes.
2, 3.
So we want to use green for growth.
Oh, we do.
I was trying to. Okay.
Oh, that's the eraser. I got it. This grows. This grows. Kelly, your cursor's like
Ah!
off.
No, that's fine. I know it is.
Okay.
Not a problem.
Ah.
Okay, yeah. So that grows and that grows. And then nobody dies, but we're going to get growth.
We're gonna get a new
Right?
generation. Yeah. So this is
Yeah.
next generation. So this is the second generation.
Yeah.
This is the current generation.
Yes.
And then we have overpopulation now. So we have some
Ooh.
things that are going to die. So I'll use red for
1,
death.
2, 3.
Oh, I like it. Okay.
So
Oh, wait.
keep in mind,
Oh,
the green
you're
aren't, the green aren't there yet.
This guy.
Right.
So no,
So 4 dies?
four or more.
4 or more.
So 1, whoops, 2, 3.
So this guy dies. This guy
Yep.
dies.
Yes.
I
Mm-hmm.
think that's it, right?
Yeah.
And
'cause
then we
this is
got
1, 2, 3.
And then we have the growth would be
growth
here.
there and there. Okay. Should we move on? Should we do that generation? So these guys go away.
Oh, awesome.
And then,
So Terry,
Okay.
Yeah.
everybody needs more time, so we're going to go
okay.
probably another 5 minutes.
Okay, sounds good. Yeah, so send me a message. Well, actually, I'll start it at 5:20. I'll
Yeah.
go back to present mode.
Yeah,
Okay.
it's 5 minutes. Yeah.
Okay.
Cool. And then I don't think. Okay. So I know a little bit enough about Game of Life that I think this is completely stable. So this is the last generation. So nothing
Okay.
changes. in the
So,
way.
so 1,
You're
2,
right.
1,
Nothing.
2, 1,
Yes.
2,
Wait.
1, 2. Okay. And then 1, 2,
Nobody
3.
gets 3.
This guy.
Yeah, this is 5. 5. 1, 2, 3, 4.
Oh, right. Those. I keep saying,
And
no, there's
5.
only. Yeah.
Yeah, you're right. Stable.
Cool. All right. So I'm gonna
Ooh.
erase this one. We
Okay.
should do. I think I'm gonna do one that I remember.
Okay.
It's
Okay.
called a glider. I'm trying to remember how to do it. So it's 1, 2,
It's called a what?
a glider.
A lighter?
Lighter? Like a
Glide.
cigarette?
Like a
Glide.
gliding.
Oh, glide.
Yeah,
Oh,
that's how we glide. Yeah.
oh, with a great song. Play it again.
Trying to remember how to do it. Okay, that's how you do it. Actually, I want to start in the other direction. I keep forgetting if I'm in the eraser or the actual pencil. It's
Oh, I didn't even see the eraser. That's cool. Ah,
Oh.
eraser. What?
Okay, so this is our first generation. What's going to happen?
Okay.
Okay. So die.
1. Yeah.
It's hard doing this with the trackpad.
Yeah. 2
Yeah.
of them are
Whoa,
these-
wrong color. Sorry.
Awesome. No, that works. That's fine, Karen.
Dies.
Okay. Yes, but I was trying to color code. Whoops.
Uh.
See. Fine. Stop.
And this is I know, isn't that crazy?
Oh, I think I started in the wrong position. Here. You know what? I'm just going to make a bigger grid.
Go for it.
It's fine. It's totally fine.
It's fine.
It's fine.
It's
It's
fine.
fine.
Why is that there? I got to get rid of that now.
Whoa.
Oh.
Bigger grid. We're going big. And then
Okay.
these lines, I think we could just extend these lines and add some more. Oh, undo. Oh, I hate this whiteboard. With the passion.
Don't blame the whiteboard.
Don't blame the tool. Blame the craftsman.
No, I blame the tool. Totally the tool.
Okay. I can try to help you out here.
So you just need the selecting tool, and then you can extend them. Okay, I'm going to add some more lines. Ah, too far.
This one is just moving it around. I don't
No.
know what happened here. Oh, I know why, because I didn't select it again. It just selected each time. There we go.
Oh, that's the wrong line. Delete that. There's two types of lines. There's like a
Yep.
yeah, the squiggly
So
line
you're
and
using the line?
the line, not the arrow line.
The arrow line.
Not the arrow line.
Not the arrow
Not
line.
the arrow
Do
line.
not use the arrow line. You'll have a bad time.
Okay.
So you can actually okay, that works. That
Okay.
works.
Ah!
I think two more, you think?
Yeah.
All right, cool.
Okay. It's not working for me.
I got you.
There. No, I got it. I got it.
Oh, she's got it. By God, she's by George.
I know. We even move it so it's a little bit more even.
All right. Okay. So we have this generation. What else is happening?
Okay. So we had a growth.
Mhm.
That's our only growth.
That's one growth.
That's
No, there's one more growth.
Oh, you're right. Right here.
1, 2, 3, 4. No, here.
Beat you to it.
Yeah.
Beat you to it.
1, 2, 3.
Oh, that's supposed to be. It's supposed to be
That's
green.
green.
It's supposed to be green. Sorry. All right. So that dies. So that one dies. That one dies. Growth. Growth. Yeah, I think that's it. So shall we?
Okay.
So I'm going to erase this guy. I'm going to erase that guy. And then we're going to color in.
Move it so it's the right place. Okay.
It's going to be the right color now.
Color in that
Okay.
guy. All right, next generation, what happens?
Okay. This one dies.
Yes.
Ooh, this one dies.
1, 2, 3.
No, this one too.
4.
1, 2,
4.
3, 4.
But, okay. Because even though it's going to be dead, it is currently not dead.
Right.
Yes. This has 1, 2, 3. This one has 2. This one has 2. Okay. Any growth? Okay. Oh, yeah, you got a growth. That's a 2. That's a growth. That's good.
This one?
Oh, it's time to start presenting, guys.
That one has 2.
Sorry, I got so caught up, Scott. I was having so much fun.
Well, that's a good thing.
All right, I'm going to start now.
Okay.
Bye.
All right, we're going back to presentation mode, guys.
Okay, well, that was fun. I was bopped around. Most of you tried using the whiteboard. I'm sorry I didn't give you better instructions. There was a grid in the background. One group figured out how to make the grid a little darker. So for next time, we'll load you up with that. But you all figured it out one way or another. So let's go through through some of the patterns and see what you all found. And you can type your answers in the chat. So for this first pattern, what did it do? What is it? What's the fate of this first pattern? The 3 in a row one. You can type it in the chat. Cycle. Yes, that's right. The top and bottom come to life, and it does sort of this. It starts out as 3 in a row horizontal, and it turns 3 in a row vertical. The end ones keep dying because they only are next to 1. So that's a blinker. It's called a blinker. It's the simplest repeating pattern. That's okay. Now what about the second pattern, the one that starts looking like sort of a letter N or something with 4 dots? If you found something, type it in the chat. What is its fate? What does it turn into? It turns into a still life, says Lee. It became stable, says Kelly. That's right. And what shape does it have when it's done? It's a beehive. That's right. It's a hexagon, and it's been called its official name is the beehive. Now, I don't know how many of you got to the third pattern. I saw one group that did. Can you tell us what happens to that? It's a blinker. Yes, it's a period 2 design. And what happens to it? The middle 2 go on and off. That's right. It's kind of cool. Well, I'm really curious if somebody constructed that or if they just found it by accident. If you took away one of the groups of 3, by the way, it would be a still life. But when you put the 2 still lifes next to each other, well, actually, that's a question. If you just had one of these groups of 3, what would it turn into? See if you can figure it out. Yeah, the squares would complete. That's right. This group of 3 would turn into a square, and then it would just be a still life. Nothing else would happen. Now, I saw at least one group figured out what this does. Can you describe what this does? It says disappear. We're talking about the 4th one. It has 5 dots in it. It rotates. So it turns into the same pattern, but in a different orientation. That's interesting. Well, I think I'll go ahead and show you what it does. So here's that pattern with 5. The 2 at the ends die, and 2 are given birth. There's 2 births and then 2 deaths, and it turns into this. That's the same pattern, but rotated. Actually, it's not rotated. What's the actual transformation between here and here? Wouldn't all 4 pieces die on the group of 3 second generation? Reflects over the axis x equals y, and then translated. That's right. So a reflection plus a translation, you know what that's called? Yeah, glide reflection. Yes, this is an example of glide reflection. So if that glide reflected, then what's going to happen next? From here to here, it glide reflected. Well, this is pretty cool. Here's what happens next. It ends up here. And that is not in the same position as the original one. So that's called a glider. And it moves across the board. It moves down the line. Well, not x equals y, but x equals minus y, I guess. So that's an example of a figure that repeats but moves as it repeats. And there are others. Here's a pattern called a spaceship. It moves directly to the right, and so it's got a lot more dots in it. I'm really curious how somebody found that. That seems very difficult to find. Okay, now all of you, I've heard many comments of, well, there must be an app on the web. Yes, there is. It's right here. And I'll put it in chat so you can all get it. This is on a web page. It's a rather small life engine. So I'll put both of these in chat. The first one says beginner life engine. That one is the one we're going to use. The other one is downloadable, and it's a much more sophisticated life engine that you can download and play with. It's called Golly, and it was created by my friend Tom Rokicki, and he taught himself computer science basically by programming that when he was a kid. Okay, so everybody go to your chat window and type on click on the first link, the one to academo.org, and you'll see a little life engine, and then you'll curse me for having you do all this work by hand and in a crazy whiteboard on-screen editor when you can just click on this. Click on this. So let's see. I guess I'll share that screen. And you can try clicking on it and putting patterns into it and seeing what they do. Let's see. Anyway, so I'm having trouble sharing my screen there. I'll go back to my slides. Oh, I have to share them. Okay, so what I want you to do, and we're going to do this in groups, is explore what happens if you put some number of dots in a row. Clear the screen. I think there's a button for that. And then put like 4 dots in a row. What happens to that? What's the fate of that pattern? Will it grow forever? Will it repeat? Will it turn into a still life, or will it disappear? Then try 5 in a row, 6 in a row, 7, 8, 9, and 10. You don't have to try it that order. So again, Terry, let's go into groups, onto tables, and we'll explore this for at least 5 minutes. We'll see how long it takes, and then you can come back and report what you found.
Okay.
Okay, who's going to share the screen?
I can.
Okay.
Go for it.
Whiteboard. Oh dear. It won't let me do Chrome tab. Chrome tab. Oh, that's a lot of Chrome tabs. That's the one. Shh. Do you see it?
Not yet.
No.
It should be.
Oh, I got it.
Yeah.
Where?
All right.
So you have to click on screen share, on share screen.
Oh, there.
Do you see me?
Maybe.
through?
Wow, that's little. Okay.
Yeah, I can make. I wonder if it will translate that. Can you see it bigger now or no?
Do I have to click? I see choices. Screen 1, screen 2. Wait, no. That's. Ooh, it wants to share my screen. I don't want to
Yeah.
share my
Don't
screen.
do that.
I don't want to do that.
So
I
you
like
should
to do
just see mine as an option, like as a webcam option. So there's me, there's Kelly, there's you, and then there should be one of my screens available to view, to click on.
Mm-hmm. What's this?
Oh, okay. So exit the whiteboard, hit the X to get rid of the whiteboard.
Ha ha.
And now we can
where it says tech support Terry.
That's the one.
Okay.
Yeah. So I tried to zoom in on my screen, but it didn't translate to the shared screen.
No.
So you'll just have to make a full screen.
Okay.
So I was gonna do start off with 4, and then advance, and it looks like it stops at the beehive.
Yeah.
You guys see that?
Yep.
Yep.
And 5 is cool. I just did 5.
Oh, you did?
Yeah.
So we have 5, advance, makes a big old square. What's going to happen next? Ooh, nice.
Ooh.
Close the centers, closes, opens. Oh, and we know what this happens, right?
Oh, yeah. Because the 3s, go vertical. Horizontal. Very cool.
Goes on.
Oh, that was
screen.
cool. That was
So
cool.
let's do that one again. I want to see that again. So
Okay, so the ends drop off, and okay, I see how it's growing, and then, yep,
the centers, and then
the centers go away,
build,
and we grow
and
more,
that, yep.
and then okay.
But that's not going to start switching yet because it's too close together. So it grows,
Oh.
and it kills it, and now it goes to the switching.
Yeah.
Okay.
Oh,
Let's do
cool.
6. Let's do 6. 4, 5, 6. Big block. So we know what's going to happen to the two in the middle. Actually, all four in the middle are going to die, right? And then two more on the ends are going to grow.
Everything except the corners is going to die, isn't it?
Yeah.
Yeah.
Nice call. Good call.
Yeah.
All right. And then we should have some growth. Where are we going to have? We're going to have growth here and here. Or I don't think anyone else is going to die.
And up in the corners too. You can't see. I'm pointing. Yes, those corners should have.
No, they only have two, right?
Oh, you're right.
So I think only here and here will have growth. Oh, here too. So these two will grow.
Okay.
Right? Because they have 1, 2, 3 neighbors.
And is anything going to die?
I don't think
I
so.
don't think so.
All right. Let's see what happens.
See.
Yeah, so it fills in. But now a bunch are going to die, right? Because it's got this one has 4 neighbors. This one has 4 neighbors. The ones that just grew are going to die. Ooh, nice. I can't go back a step, can I? All right, and then it's going to grow here and here.
And on the outside.
Yeah, these 3 are going to grow.
And the outside.
And here and here. Yeah. Yep. Here, no. None are going to die.
Yeah, the lonelies are going to die.
Because there's
you're
only
right.
2.
Yeah, you're right. Nice. Call, good call. So these 2 are going to die.
Yes.
And then these are going to come in.
And on each side of the little knobs too are
Yeah, those are going to come in. Nice, yeah.
Oh, okay.
And then these are going to grow. All of these are going to grow in.
More knobs on the knob on the outside.
Yeah, these are going to die. And
Yeah.
these are going to come in here. That's a big switch. Pretty much everything changed.
Where's the way back button or the go back? Okay.
I know. I'm just going to keep going.
Okay.
Oh, that was a big step.
Okay. So it's
Oh. Everything dies.
So,
okay, do that again. Do 6 again.
It was going.
How many steps did that take? Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Wow.
12 steps.
That was cool.
That was cool. All right. I want to do 10.
Okay.
Big block. That seems to be so it seems every row goes to a block.
Oh, because
Because the ends are gonna drop off, and then
the others go,
and then a new row appears.
And then everything in the center is safe because it has at least 2 neighbors.
Yeah.
And then it explodes from there.
And then it goes away.
And then it.
Ooh.
Ooh.
Hey, Scott.
Hey, how you guys doing?
We're at 10. We skipped a few.
We skipped
Go back to
79.
7, 8, 9.
And yeah.
Let's do 7. Let's do.
Everybody's.
Whoa. Okay. Sorry, say that again, Scott.
I think like 2 more minutes should be.
Okay.
Yeah.
Okay.
Yeah. Because this is just This
It's
is
fun, but I want to show some other stuff.
Right.
Let's do 7 again. That was cool.
I do suggest you try 10.
We did.
Yeah, we did 10. We just
Yeah.
All right. So
Okay, see
big block. It always goes to a big block.
And then
And splits apart. And then it's gonna come back in because it explodes and contracts, but also builds on the outside. And then a bunch are gonna die. And then a bunch are gonna come back inside. It's gonna
back inside and outside. Yep.
And then explode. So it seems to have like kind of contracting.
Yes.
It builds and dies and builds and dies.
Yeah, the outer edge, they're new outer boundaries, but we regain stuff on the inside.
But that causes a critical mass. So it's kind of like populations, right? Where you have population growth, lack of food, population decline, population growth, but it's never like Okay.
But okay, I was going to say that last one, nothing was going to disappear. Okay, because the little thing in the center is pretty stable.
Mm-hmm.
Yeah.
Yeah. Okay, keep going.
Okay, it survived that.
Now stuff's going to
So
happen.
it's pretty stable. Interesting.
Yes.
Yeah.
But now things are going to grow and die.
Yeah. How
And now
long
it's
is
no
that
longer
gonna-
stable.
Oh, now it's not stable anymore. Nope.
Yep.
All goes.
God.
And then the ones in the ends are going to die here. Oh, no,
Uh-huh.
because there's 3. Yeah.
Oh, and then we have the okay.
Okay.
That's it.
And then there it
Oh,
is.
and nothing happens. Okay.
I want to try something. So 1, 2, 3, 4. 1, 2, 3, 4.
Okay.
Perfectly stable. Okay, cool. I was just curious. Snowflake works.
Oh, technically a snowflake has 6.
It has 6.
Yeah, 6 instead of 4.
Ah,
Well, if you want to be technical.
technical. Cool. Okay. I'm going to bring us back.
Okay.
Okay.
All right, I should make the announcement. Present mode. It's not just jarring.
And then the limo comes.
All right.
Okay. So let's go back to let's you can type your answers in chat. What happened with 4? What was the fate of 4? You can type it in chat. Turns into, and it was a beehive. And what about 5? A blinker. And what about 6? 6 dies. That's interesting. 7. Anybody try 7? What happens to 7? It stops. Yeah, it's a still life. And 8. 4 beehives. Yes, the official name of that is a honey farm. 9. What does 9 do? I think I remember that's a still life. Or is a blinker? It's a pair of blinkers. Okay, 2 blinkers. And the general word, by the way, is oscillator. But it might have a period of more than 2 states. And what happens to 10? Did anybody try 10? Liz says it cycles. Oscillator with a longer period. Did anybody find out what the period was? 14, says Madavi. Yeah, it's surprising how long the period is. So you can explore these on your own. It's one of the natural first things is what happens. I don't know what 11 does. One comment though, this particular life universe is not an infinite plane. I said it's supposed to be played on an infinite checkerboard. This one wraps around. So if a pattern goes off the bottom edge, it returns on the top edge. Topologically, that's like taking the top edge of the piece of paper and joining it to the bottom edge. So that would be like wrapping it into a tube. Of course, the left and right edge are also wrap around. So you take that tube and stick the 2 ends together, and you know what sort of figure you get when you do that? You know what that's called? Yeah, it's like the game of asteroids. That's called a torus. Taurus is the bull, but Anyway, that's it. I guess that's the horns of the bull there. Yeah, that's right. That's a torus. If you can go deeper into it, if you were to identify two edges with a twist and the other ones, if this straight and the others with a twist, you get a Klein bottle. There's a lot of fun things to do. Yes, the game Asteroids was played on a torus. Cool. Okay, let's go to a few other things I want to mention, because we have about 15 minutes left, and I will leave a little time for questions. Let's see. I don't know if there's a way to do this with. Can you turn on everybody's mics? Because it's a little awkward for me to read chat at the same time. And Terry, is there a way to do that?
No, unfortunately. Aside from
okay, so why don't you relay? Type in chat. Here's the big question. What are, and this is the meta question. I'm going a little bit fast, but it's a really deep question. What are some interesting questions to ask about the game of life? The things you're curious about, but you don't know the answer. And please type your questions in chat, and Terry, you can relay it to me, and I'll write it down.
Can you make a non-repeating infinite pattern?
Make a non-repeating infinite pattern. Cool. Any others?
So I was actually kind of curious with this, the way it wraps around.
Yeah.
Can you make it so that you make a pattern that changes its angle? So it starts off wrapping around from top to bottom and then meets itself and starts changing, going left to right. But that might be not specific to life, more to that version of life.
Wrap around life.
Someone asked, infinite growth possible?
Yeah, is infinite. Yeah, because an infinite non-repeating pattern is infinite growth possible? Yes. That was the first question that Conway posed. He gave a $50 prize, and it was won. And I'll show you the winning pattern in a moment by a group from MIT that included the mathematician Bill Gosper, who became one of my mentors.
Graham asks, what is more common, repeating, terminating, or still life?
That's an interesting statistical question. I haven't heard that question. More common, repeating, disappear, or still life.
David
asked that as a statistical question.
David Austin asks, can you find oscillators of any period? And I think he means
oscillators. Yeah, that's an interesting. One thing for sure is if you have two prime oscillators and you have them go side by side, you've got the period that is the product of the two oscillators periods. So you really only have to answer it for prime numbers.
Kelly asks, what can you work backwards from a desired shape?
Yeah, that's a really interesting. And that leads, I'll just insert to the Garden of Eden question. Is there a pattern with no predecessor? That was my favorite question when the first Life article was written.
And then Liz asks, in relation to Graham's question, how often does total death occur?
Yeah, how often does total death? Now, the reason I raised this is I think a great thing to do in math class is to ask kids, what are your questions? One of my favorite math teachers, Marion Walter from the University of Oregon, starts her favorite question is, look around. What are some questions? It's so incredibly open-ended. And you go, about what? And she says, well, look around. We're in a ballroom. Usually she's giving a talk, so there's a lot of repeating patterns. What are some things you're curious about? I think it's a great thing to do. And it's a natural thing to do, and it's a good thing to encourage. And it's okay as a teacher if you don't know the answer. That's the important thing that unlocks this Pandora's box. Well, anyway, I want to show you some of the other cool things in life. And here's some still lives. We saw the boat. There's a loaf. Here's some common repeating patterns. On the right, we have the what 10 in a row does. So it's actually period 15. So you're very close, Madavi. There's a pulsar with period 3 there. Anyway, some other patterns. Here's some spaceships, gliders and spaceships of different sizes. Not quite sure why the spaceship pattern, if there's an even heavier weight spaceship. Here's the pattern that won the $50 prize of a pattern that grows forever. And you can see it's made of parts. This is called the glider gun for fairly obvious reasons. It's made of two figures called shuttles that tend to, and the shuttles, when they hit blocks, reverse direction and come back together. And when the two shuttles hit each other, there's some debris in the middle that results in a glider. So it's creating a glider stream. Here's an incredible, I'm jumping to a much more complicated thing. Okay, what we have is a whole flotilla of spaceships that are leaving debris. And the debris they leave is a stream of glider guns. So this is and each of those gliders, the glider guns then starts emitting gliders. This is a pattern that does not grow linearly. It grows as n squared. So it grows, that's another question you can ask, is how fast asymptotically does your pattern grow? And the patterns just get more and more complicated. People have gone to ridiculous extremes. This is a small computer that uses gliders to communicate bits of information. And people have built entire computers within the game of life. Now, I want to talk briefly about some of the theory behind it. Life is an example of a cellular automaton. That is, it's an example of a cellular automaton in general has a grid of squares, and each square can have some number of states. And then there are rules for how the universe changes from one state to the next. Of course, it could be just on a line. It could be three-dimensional. It could be on a hexagonal grid. It's called an automaton because it acts automatically. Cellular automata were invented before computers, and they were invented around in the early part of the 20th century, about 100 years ago, when people were just starting to think about computers. And certain people, John von Neumann was one of the inventors of the electronic computer, and he wondered early on, can a machine build a copy of itself? Computers were really crude then, so he built a theoretical model. He was influenced by Stanislaw Ulam, another mathematician who was studying cellular automaton as a model. He was modeling chemistry. He was interested in how fluids flow. And they created, here's another cellular automaton created by my friend Brian Silverman. It's called Wire World. It's for simulating the flow of electricity. And it has some clever rules. And the rules are such that you can create, here's a diode, which will there's white and blue dots, and the rules are such that if you have white and blue next to each other, white tends to be the leading edge and blue is the trailing edge. So blue tends to turn back into the wire color, and charge will flow. But this particular construction will allow flow to go in one direction, but not the other. And you can create logic gates using these rules. Here's an OR gate, an XOR gate, and an AND gate, all the logical operations. And from these are the building blocks of building a computer. Here's a small computer that's built in Wire World. So it's got a digital display up at the top that will display numbers. It's got a binary to binary coded decimal converter. Really crazy stuff. This is what people are doing now, but in the early days, they were using it to imagine what is computable. If you saw the movie, you know about Alan Turing, and you saw the movie, The Imitation Game. He was thinking about the Turing machine itself is very closely related to Cellular Automata. Here's some other copies, crazy Cellular Automata. This one deals with fluid flow. This one's three-dimensional. This is the answer to John von Neumann's question. He was able to build a cellular automaton that built a copy of itself. Actually, it starts with two copies of itself. One of them is program and one is data. It says, looks at one of them and says, here's this automaton acts on this one. It says, looks at its structure and builds a copy. Here's what they look like in animation. They're really visually pretty incredible. The particular rules of life are particularly rich, but there are many other rules you can try. Some of them just everything will die. Everything will grow. Life is somewhere in between order and chaos. John Conway himself wasn't that interested in the game of life. He didn't pursue it that deeply. He just said, because he knew that it logically had all these properties, and he didn't want to put in the time to explore it that fully. There are some incredible movies on YouTube. I'll send you this in chat, showing some of the absolutely incredible constructions that have been built in life. Here's the streams of gliders that come together and build a very complex spaceship. So you can collide gliders to make other things. I'll put that in chat here. Yes, David Austin, is there other versions of I guess I'm asking this. Is there any theory developed on how to create patterns other than, yeah, okay, those are the questions from earlier. I'll go through it. So that movie is in chat. Here's all the references. You can read more about cellular automata. I guess I would think a lot of why I wanted to include life is that mathematics and computer science are very closely related, and yet they kind of diverged. And mathematics, as it's taught, tends to not acknowledge computer science, which is kind of weird. And then computer science, it's almost they're closely related, yet they kind of ignore each other. Curious thing. There's anyway, so I'll leave some time for questions, but and then I'll just mention that, let's see, Terry, could you relay any questions? Are there any questions? Please type your questions in chat if you have any. Can you go back to the resources guide? Yeah, I'll leave that on the screen, definitely. So that was silly of me to skip over that. Here it is. I hope that's readable. Maybe.
Yeah, they can make it full screen if they need to.
Yes, you can click on the upper right corner and make it full screens. And we're gonna, Terry, can you we can send out a follow-up email with all these references, right?
Yeah, we can.
And I want to send out the slideshow too. Okay. Okay, well, if there are no more questions, then thank you very much for your time. I will mention a couple other things. And in addition to doing these talks, I'm also running a group called Math Monday. It's on the mathcommunities.org website, along with Math Circles. And we're all sponsored by the American Institute of Math. And I'm now, for the summer, putting out a weekly puzzle. If you want to get a puzzle in the email, sign up at mathmonday.net. Here's one of the puzzles. How many squares of any size are in this figure? Of course, if you're just counting the small squares, there's 16, but I'm counting, asking for all squares of any size. So can you figure that out? You can type your answers in the chat. Anyway, that's one of the puzzles, and Well, thank you so much for coming. I really appreciate your participating, and I hope you learned something and can take some of that back to your classroom. Take care, everybody, and enjoy the rest of the show. And do look up John Conway. There's some fantastic videos about him on I think that's one of the references as well, of him talking about the game of life. He's a very entertaining personality. There's even a whole book written about him. Okay, take care and enjoy the rest of the week.